applications of magnetic forces. So, you might recall way back when in electrostatics, I told you how TVs used to work with something called a cathode ray tube. Those were the TVs that had that big bulge sticking out the back. That was actually an electron gun, a cathode ray tube. And then I told you we deflected them using charged plates. We don't. Actually, we use magnets. We use solenoids to deflect the charges coming out of a cathode ray tube. Pause for a second. Why do we use solenoids instead of long parallel plates? If we orient the solenoids vertically, it meant the back of the TV didn't have to stick out as far. It allowed you to shrink things down a little bit. So here is a diagram right here. Here are two solenoids. We have solenoid M and solenoid N. Now we can have current either in solenoid M coming from W or from X. And the question here says solenoid M, this one, can deflect the electron left-right or up-down? That's a good question. So it's going to depend on what direction the magnetic field is right there. Let us hold the solenoid in our hand, solenoid M, and you can hold it either that way or this way because I don't know which way the current is going. But here's what I know. Let's pretend there is a north pole there. Let's imagine that. And let's imagine a south pole there. Magnetic field lines point from what to what? So if I exaggerate a long magnetic field line, don't write this down, just watch. That goes off the page. Right here, where the electron is traveling, I'm going to argue the magnetic field is pointing in which direction? And I'll even say down the page if we're going with our three-dimensional reference. You see that okay? All right. So now let's figure out which way that would deflect an electron. Deflect a what? We don't deal with electrons because they're negative. So in this picture, it looks like the electron is coming out of the page towards us. What's that the same as a proton doing? So let's use my big board here. Point your thumbs into the board. Which way is, we're using our right-hand motor rule, so we're going to do the high five. Don't curl your fingers, high five. Which way is the magnetic field? Down. So you know what? The vertical solenoid can deflect the electron to the left, or if I flip the current, it can deflect the electron to the... So a vertical solenoid does a horizontal deflection. Okay? This is what we're going to write then. Solenoid M can deflect the electron horizontally, left or right. Similarly, solenoid N, it's going to send out either a magnetic field north-south going like that, or if I flip it, going to the right. So we have an electron coming out of the page. That's the same as a proton. Right hands with me, folks. Going into the page. Right hands with me, folks. Good. And we can have a magnetic field pointing to the left. That'll deflect the electron up. Or if we flip the current, we can have the magnetic field pointing to the right. That'll deflect the electron down. So a horizontally oriented solenoid can deflect the electron vertically, up or down. If you ever see like an old TV at a garage sale for like $5, by old, I mean the ones with the big thing sticking out the back, you can buy it and take it apart. The only thing is you need to leave it unplugged for about a month before you start taking it apart. There are very strong capacitors inside old televisions that can store enough charge to injure or kill you if you don't let them slowly discharge by just slowly with humidity giving their charges off into the air. But once you've left a TV unplugged for about a month or so, take it apart and you'll kind of see the parts inside. It's kind of an interesting thing to do. Put your pencils down, look up.
This syringe contains a radioactive form of glucose known as FDG. The doctor will soon inject its contents into her patient's arm, whom she's testing for cancer using a PET scanner. The FDG will quickly circulate through his body. If he has a tumor, cancer cells within it will take up a significant portion of the FDG, which will act as a beacon for the scanner. PET tracers such as FDG are among the most remarkable tools in medical diagnostics, and their life begins in a particle accelerator, just hours earlier. The particle accelerator in question is called a cyclotron, and it's often housed in a bunker within hospitals. It uses electromagnetic fields to propel charged particles like protons faster and faster along a spiral path. When the protons reach their maximum speed, they shoot out onto a target. That contains a few milliliters of a type of water with a heavy form of oxygen called oxygen-18. When a proton slams into one of these heavier oxygen atoms, it kicks out another subatomic particle called a neutron. This impact turns oxygen-18 into fluorine-18, a radioactive isotope that can be detected on a PET scan. In a little under 2 hours, about half the fluorine will be gone due to radioactive decay, so the clock is ticking to get the scan done. So how can fluorine-18 be used to detect diseases? Radiochemists at the hospital can use a series of chemical reactions to attach the radioactive fluorine to different molecules, creating radio tracers. The identity of the tracer depends on what doctors want to observe. FDG is a common one because the rate at which cells consume glucose can signal the presence of cancer, the location of an infection, or the slowing brain function of dementia. The FDG is now ready for the patient's scan. When a radio-labeled tracer enters the body, it travels through the circulatory system and gets taken up by its target, whether that's a protein in the brain, cancer cells, or otherwise. Within a few minutes, a significant amount of the tracer has found its way to the target area, and the rest has cleared from circulation. Now the doctors can see their target using a PET, or positron emission tomography, scanner. The radiation that the tracer emits is what makes this possible. The isotopes used in PET decay by positron emission. Positrons are essentially electrons with positive charge. When emitted, a positron collides with an electron from another molecule in its surroundings. This causes a tiny nuclear reaction in which the mass of the two particles is converted into two high-energy photons, similar to X-rays, that shoot out in opposite directions. These photons will then impact an array of paired radiation detectors in the scanner walls. The software in the scanner uses those detectors to estimate where inside the body the collision occurred and create a 3D map of the tracer's distribution. PET scans can detect the spread of cancer before it can be spotted with other types of imaging. They're also revolutionizing the diagnosis of Alzheimer's disease by allowing doctors to see amyloid, the telltale protein buildup that otherwise couldn't be confirmed without an autopsy. Meanwhile, researchers are actively working to develop new tracers and expand the possibilities of what PET scans can be used for. But with all this talk of radiation and nuclear reactions inside the body, are these scans safe? Even though no amount of ionizing radiation is completely safe, the amount of radiation the body receives during a PET scan is actually quite low. One scan is comparable to what you're exposed to over 2 or 3 years from natural radioactive sources like radon gas, or the amount a pilot would rack up from cosmic radiation after 20 to 30 transatlantic flights. Most patients feel that those risks are acceptable for the chance to diagnose and treat their illnesses. If you think scanning the human body is as fascinating as we do, check out this lesson. Otherwise, here's a playlist on other fascinating technologies that'll spark your curiosity.
So there's one nice application. And yeah, most hospitals do have a particle accelerator somewhere. Example 1. An undeflected electron beam strikes the center of a cathode ray tube. A solenoid placed beside a cathode ray tube causes the electron beam to strike the screen at position X. Okay, so normally it hits right here, but now it looks like it's been deflected down. What changes to the magnitude and direction of the current in the solenoid would cause the electron beam to strike the screen at location Y? That's a good question. Let's look at, first of all, current direction. If we want to have a vertical up deflection instead of a vertical down deflection, what do you think has to happen to the current direction? So, no, yes, no, yes. What would increase the deflection? Well, remember, the force on a charge is QVB. You're not going to change the charge. It's an electron. They're coming out at the same speed. How could you get a bigger force and therefore a bigger deflection? Bigger magnetic field. So, how can you get a bigger magnetic field? We said the magnetic field in a solenoid was equal to mu naught N times I over L. Did we change the actual solenoid, the number of coils? No. Did we change how long the solenoid? No. What could we do? Bump up the current. Yes, yes, no, no. Correct answer is B. With the electromagnet turned off, it says, electrons in a cathode ray tube strike the center of the screen as shown. When we turn the electromagnet on, where will the electron beam now strike the screen? It's a little bit tricky to see because it's a black and white photocopy and it's a bit blurry. So I'm just going to do a little sketch of the solenoid right here because I don't know which way the current is flowing. Well, yeah, it looks like the current is going. Am I correct? If I'm looking at it, it says the positive is on top. So I wrote this one badly. That should go behind. Excuse me. I think that's the direction the current is going. So I'd like to know which end of this solenoid is north. Get your right hands ready. Now we're going to use the solenoid rule. You're going to pretend you're holding the solenoid in your hand. You're either going to hold the solenoid this way or this way. You can't hold it this way because it's oriented vertically. You're going to you can't hold it this way because it's oriented vertically. You're going to curl your fingers in the direction of the current. So, could I hold my hand that way with my thumb pointing down? Doesn't work. It's got to be this way, right, Owen? Okay, you're following along. So which side of the solenoid is the north pole, top or bottom? So let's put a little N right here, a little S right here. Or if you didn't redraw it, put a little N right here, little S right there. Magnetic field lines point from what to what? So I guess this magnetic field line would go. You know what? Right there, which way is the magnetic field pointing? I'm looking for a two-letter word that starts with letter U. Okay, now I know what direction the magnetic field the electron is going through is. What direction is the electron traveling? Please be obvious from the picture. What direction is the electron traveling? Up? Out of the page. Did I say electron? We don't deal with electrons. So an electron coming out of the page is the same as a proton traveling which way? So point your right thumbs into the page. Oh, this is the right-hand motor rule, the three-dimensional one. So your hands are like a high-fi now. Right thumbs into the page. What direction is the magnetic field? Up. So somehow I'm going to have to hold. For me, because I'm facing you, it works pretty good. I guess for you folks, you'll have to, you know what? If you hold your hand out kind of like that, I think that works. Yes? What direction will the electron be deflected to? 1, 2, 3, or 4? Not only can we use this for television, which, raised most of you since children, but we can use this to run electric motors, which I suspect in your lifetime are just going to become even more important all the time. So I'd like you to imagine that we have a rigid wire loop placed in a magnetic field. Braden, which way is the magnetic field pointing? To the... Okay, so magnetic field is pointing to the right. And we've hooked it up to a battery, so let's draw in the current. It looks like the current is flowing that way. Add those arrows, please, for the current. And it says, determine the direction of the current in each segment of the loop. We just did that because I couldn't help it. It was a habit. And then the direction of the force on each segment. So look at segment 1. That's the bottom segment. Segment 1 is horizontal. You agree with me, Zach? And the magnetic field is also horizontal. You agree with me? Remember, we said that for a wire to feel a force, it has to be traveling perpendicularly to the magnetic field. So how much force will segment 1 be feeling? You can be taught. Segment 2 is much more interesting. What direction is the current in segment 2? Good. What direction is the magnetic field? Use your right-hand rule. This time I'm not going to give you any hints. See if you can figure out. It will feel a force. What direction will segment 2 feel a force? Into the page? Is that what I'm getting? Okay. So, into the page. Zach, what about segment 3? Good. What about segment 4? Well, now it's coming down the page, magnetic. It's going to feel a force out of the page. And so what's going to happen is on segment 2, it feels a force into the page. On segment 4, it feels a force out of the page. It's going to start to spin. This is the basis behind an electric motor. It's going to want to spin. A bit of a problem with this system, though. As soon as segment 4 gets to this side, now it's going to feel a force up. And what would happen is this would spin one turn and come to a stop. Unless we can figure out a clever way to always make sure that the current on this side is going up the page, and always make sure that the current on this side is going down the page. How the heck can we do? Yeah.
Do you want to do it?
No. Nikola Tesla came up with one, but others have. In fact, Michael Faraday is the person who probably came up with this, I suspect. So, will the loop tend to rotate? Yeah. But only with this current set up a half rotation. So what's the secret? It's something that we call a split ring commutator. You say, what? Show you. I got a better view, a side view. So figure 7.28 shows a simple one-turn coil motor operating on direct current. What we do is, instead of having wires transmit the current, we have a metal brush right here. Look up, Danica. And a metal brush right here. So as long as the metal is touching this piece of metal and this piece of metal, current will flow. But basically on the end here, we have a cutout. What we really have is that. Think a hamburger patty, hamburger, but no patty. 2 hamburger buns. And what happens then, well, let's follow this. First of all, which way do we have the current flowing in the left arm right now? Into the page. What direction is the magnetic field? Magnetic field lines always point from what to what? North to south. So the left arm is going to feel a force down. Yes? Okay. What about the right arm? It's going to feel a force By the way, we call this an armature, a loop of wire, the thing that's moving inside the motor. We call it the armature. Oh, you want to make the motor stronger? Put 2 loops. Now you've doubled the strength. You want to make it even stronger? 3 loops. Now you've tripled the strength. It's a direct 1-to-1 ratio with because each wire feels a force. So 2 wires, twice the force. 3 wires, 3 times the force. Okay. Or if you really want to get clever, replace that with a solenoid. We'll talk about that in a second. Okay. Once this does a half turn, here's an end view. You might need to turn the page. Now, this particular picture, instead of rotating a loop of wire, we're rotating a solenoid, like that motor that I briefly showed you yesterday that I'll bring back. But notice what happens to the current here. Once we get about halfway through, you know what? I have an animation. I think that shows this better. Okay. Here's our electric motor. And in the middle here, we have a gap right there. Right here on the left and right here on the right, we would have a little wire brush, something with very little friction, but it's conductive, so it's transmitting current. And if I stop the motor right here, let's follow the current. Look up, Owen, look up. Current going this way, flowing through here. Current will be going into the page, magnetic field that way. This arm feels a force up. This arm feels the force down. This gap is so that when the arm gets right to here, no more current is flowing, but its momentum carries it over, and it manages to now reconnect. And if you watch, you'll see always the current on the left is going to be coming out of the page towards us, and it's always going to be feeling a force down. Always the current on the right is going to be into the page away from us, and it's going to be feeling a force up. We've come up with a clever way from a direct current source to alternate it. Okay. That's the basic electric motor. Now, the weakness of this is if you shut the motor off and it comes to a stop right there, because it slowly spins and winds down, and it comes to a stop right there, then when you turn it back on again, there's no net force, and so it won't work. So most modern motors, instead of a rectangular single loop, they have 3 loops aligned at 120-degree angles from each other, so there's no way that you can ever get a net force of 0. There's no way you can get this situation. But that's how it works. I think I got another one, side view. Good morning. Bear with me. I got to pause my recording now and interrupt YouTube for a student who's late.
Torque in a DC electric motor is
Here's
created
a nice
by
view as well. Hang on. I think I
magnetic
can pause
forces
it. Nope, I'm going
exerted on the electric current carried by the rotating
And you can see
part
the
of the
importance
motor.
of what we call the
In
split
this
ring
virtual
commutator.
model, the flow of
That's what
conventional
allows the
current is
motor to
represented by
always
the
have
red
the
balls.
current flowing
Magnetic
on the same
fields are
side in the
represented
same
by the
direction
blue lines.
again. Or the other option,
The
by the way,
current
hook it up to an
experiences a
alternating
torque
current
due to the
source. But we're not
offset
looking at that
forces
right now.
on
We're
the
looking at
top and
direct
bottom
current.
sections of the loop.
If you hook it up to an alternating
Forces
current
on the
source,
front and
the
back
problem with that
segments
is
of the loop
the
exactly
motor's
cancel,
speed
so
will
they
be
do
the
not
frequency
contribute
of
to
the
the net
alternating
torque of the
current.
loop.
You can't control it. Here, I can control the speed by just
battery that
increasing or
drives this
decreasing the
motor
current, because
produces
that'll
a
increase or
constant
decrease the
voltage,
force,
which can
which will
only
increase or
drive the
decrease how
current
fast the
in
loop
one
goes.
direction.
So these are much more controllable.
However, the motor loop would get stuck lined up
The
perpendicularly.
electric motor. So that's what these pictures were trying to illustrate. Let's read through this. So it says the split metal cylinder on the armature is the split ring commutator. That's that thing right there. Think of it as a hamburger minus the patty, and the buns are made out of metal. Current direction is from the brush at A to the left half of the commutator, then to the coil of wire. Current direction is such that the left end of the armature is a north pole, the right end is a south pole. Basically, this allows us to always keep the direction of the current flowing the same way. Electric motors come in all sizes. Some are very, very tiny and drive little toys. Others are huge and drive trains or buses or Teslas. You can find electric motors in trains, automobiles, clocks, wheelchairs, pretty much anything nowadays. If it's moving and it's not using an internal combustion engine, it's got an electric motor, right? Elevators, big electric motors, cement mixers, furnace fan, any fan that's an electric motor, many other devices. So the ones I've showed you operate on direct current. Alternating current motors work on essentially the same principle. They don't need the split ring commutator. Since the current is already alternating, there's no need to somehow manage to flip the current manually. Pause here. So what's your homework? You're not going to do every question on this particular review. So you can cross out number 1, or you can just jot this down and find it later. Okay? Not wild about number 2. Three is good. They're asking you to find the magnetic field. They've given you the radius. Oh, I think magnetic force is what's pushing me in a circle. I'll start there. And probably solve for B. Then, as a follow-up, now they're going to tell you something about the solenoid that's causing that magnetic field. So you'll either, now that you know B, you can either solve for little n, or big N, or I, or L, depending on what they give you. That would be a good question, fair game, as far as I'm concerned. You can skip 4. 5 is good. 6 is good. 7 is good. You can skip 8. 9 is good. 10 is good. You can skip 11. 12 is good. Yeah, you can skip B. 12B. 13 is good. And I'd like you to all look at number 14, please, because this is also a very cool application. Here we have a circular loop of wire carrying current. First of all, what direction is the look up. What direction is the magnetic field? What do those X's mean? Into the page? Okay. At the top here, what direction is the current flowing? So point your thumbs to the left. Magnetic field into the page. Which way will the top feel a force? Which way will the bottom feel a force? Which way will the right side feel a force? What will the left side feel a force? This will cause this to contract. It will actually cause it to shrink. In a few minutes, I'm going to show you a video where we put a quarter, a round conducting surface, into this, and you'll see, you run a massive current through it, the quarter gets smooshed together and shrinks. You can shrink things. Not like Honey, I Shrunk the Kids, but you can shrink things. Okay? So I talked about number 14. 15 is good. You can skip 16. You can skip 17. 18 is good. 19 is good. 20 is good. 21 is good. 22 is good. Some of these you've kind of already done on the homework, but you can refresh your memory. 23 is good. 24 is good. 25 is good. 26 is good. 27 is good. That's just plug and chug. 28 is good. 29 is good. 30 is good. Skip 31. 32 is good. Skip 33. Skip 34. And the scholarship questions are cool, but you don't need to do those if you don't want to. You'll get time. So your other homework yesterday, I gave you a take-home quiz on right-hand rules. Try that today. On Monday, I'm going to be giving you another take-home quiz. It's going to be having all sorts of questions on F equals Bill, F equals QVB, and solenoids. And I'll give you some pretty blatant hints Monday and Tuesday about the kind of questions you'll see on your test on Thursday.